Let's look at how many gates we had to do in order to do this. So I'm going to show that we could do this using, at most, 4 times 2 to the k gates. So we're going to do this by induction, so we're going to have a base case, where k is equal to 1. In our base case of k is equal to 1, we required 3 gates. And it was 3 gates because if required 3 gates. We said lookup 1 was just the same as if required 3 gates. So our base case where k is equal to 1, that requires 3 gates as well. How many get that? Okay, so now we're going to have our inductive hypothesis. Our inductive hypothesis says, let's assume the number of gates for lookup sub k minus 1. We want to show that that is going to be less than or equal to, at most, 4 times 2 to the k minus 1. So we're going to assume that this is true, and then what we'd like to do is I'd like to show that the number of gates for lookup sub k is less than or equal to 4 times 2 to the k minus 1. Sorry, forget the minus 1. 4 times 2 to the k. So that's what we'd like to do. So in order to do this, let's identify in terms of lookup sub k minus 1 how many gates lookup sub k is going to need. So when we did lookup sub k, the number of gates we used, well, we had to do, if we look at this, we had to do 2 lookup sub k minus 1s. So we had to do our k minus 1 lookup twice, and then we had to do an if. However many gates lookup sub k minus 1 required, we're going to do 2 times that, and then we're going to add 3 more gates for that if. So if lookup k minus 1 requires however many gates, twice that plus 3 is how many gates lookup sub k requires. Our inductive hypothesis said that this was less than or equal to 2 times 4 times 2 to the k minus 1 plus 3. This is equal to 4 times 2 to the k plus 3. And why do I have an extra plus 3? Yeah, I definitely did something wrong here. What did I do wrong? Essentially, the idea is that we require roughly twice as many gates to do lookup sub k as we had to do lookup sub k minus 1, because we had to do 2 lookup sub k minus 1s in that situation. All this exercise of doing syntactic sugar is to show you that we can start doing more and more and more complicated types of functions using only NANDs. So everything that we've discussed, we now know that we could do all of that using exclusively NANDs. The next thing we're going to do, next class on Thursday, is we're going to use this syntactic sugar in order to show that NAND is, in some sense, universal. And in this case, when we say universal, we mean that we're going to be able to use only NANDs to compute any finite function at all. So no matter what finite function you want me to implement, we know that we can do that using only NANDs. So NAND circuits, they can do any finite function ever, is what we're going to show next class, which is going to imply that and or not circuits can also do any function ever.